Hello, everyone. Good morning. Yeah, so thanks, Andre and Tarcisio and Martin for the invite for the presentation. So I'll present a work that we recently got accepted in VTC 2024. So this work was just presented yesterday in the US by Professor Walter, and I'll be presenting here for you. So the title is Power Allocation for Uplink Sensing and Communication in Cell-Free ISAC Systems with Multi-Antenna Users and Multibeam. So we have here the authors of the paper. So Igor Pagliano was the first author. He's an undergraduate student and he's now in France. And then I was also an author. We have Yuri Gabu-Fodor, who's our contact in Ericsson for our project. And then we have Professor Walter and Michelle, who is a PhD student in GTEL. Mouse. Okay, so I'll start with a little bit about the background and motivation. So what we have seen in most works from the literature on ISAC is that we have what we are calling the network-based sensing, which is basically the case when the APs are transmitting the sensing symbols, right? And we also have the counterpart, which is the UE-based sensing, which is when the UE is transmitting the sensing symbols. And then we've seen that most of the works are focusing on the network-based sensing, and then we wanted to study the case of when the UE is transmitting the sensing symbols. And it might be called UE-based sensing and also uplink sensing. I mean, that's two terms that we see in the literature and also within Ericsson. So basically, we wanted to analyze the performance of ISAC systems when we have this UE-based sensing. And then we are considering this cell-free network with ISAC in the uplink. And then we have multi-antenna UEs transmitting both communication and sensing symbols. And the UEs are adopting a multi-beam scheme where they use one beam to transmit the communication and another beam to transmit the sensing symbols. And then for this work, we are analyzing two classic methodologies for the beamformer at the UE. So we are using an SVD beamforming and also an angular beamforming. I'll provide more details about them in a few minutes. And then we are performing some analysis when we vary the power allocated to the sensing and the communication beams. So this is the scenario that we have. So as I mentioned, the multi-antenna UEs transmit both unknown communication symbols and known sensing symbols. So they act as the TXC, which is the transmitter for the communication, and the TXS, which is the transmitter for sensing. And then we have two independent groups of APs. So we select a group of APs to act as the sensing receivers, and the remaining APs will be the communication receivers. So this basically means that we don't have an AP performing both functions at the same time, right? So this is one approach. We also have other approaches where the AP performs both functions. And then for this work, we are considering perfect CSI, which is assumed to be known at the CPU and the UEs. And then we also assume that the previous processing was done to know the region where it's most likely for the target to be. So we do not assume that we know the target position, but we know at least a region where the target might be. And then we are considering that regular setup. So in that example, you have the target in red, right? And then we have here the orange APs, which will be performing the sensing. And then some UEs, which are here in green, will be transmitting the sensing signals that will be reflected by the target and arrive at the APs for the sensing purposes. And this is a little bit about the frame structure that we have. So if we consider the APs, so here we have the APs and the UEs, and then we see that the UEs act as both communication transmitter and sensing transmitter, right? As they are transmitting sensing symbols and communication symbols. We are assuming that the sensing symbols are used exclusively for, the symbols are used exclusively for communication and also exclusively for sensing. So these are different symbols. It's not the same symbol. And then the AP is not transmitting anything. And we have separate APs used for communication receiving and sensing receiving. Okay, so this is the signal model that we have. So it's basically a classical uplink signal model. And then we have here, this is this signal received at the AP. And then here we have an illustration of the beam transmitted by the UEs reflected at the targets and arriving at the APs, the sensing APs. And we are also indicating here the interference caused by the echoes reflected at the targets on the communication APs. And here we have the communication being transmitted by the UE. So this is the channel model that we are using. So it's like based on the steering vector. For the communication channel model, we have here the large scale fading, and then we have P paths here, and then the angle of departure at the APs and the angle of arrival at the UEs. And then this is the structure of the steering vector. And we have a similar structure for the sensing channel. But here we have that the steering vector is also weighted by the radar cross-section power, which is this alpha here. And we have here the L targets that we might have in the system. So these are the two beamforming techniques that we are using. So for the SVD beamforming, we are stacking the channels of the all the APs for a given UE vertically to arrive at this stacked channel here. And then we apply an SVD and get the first column of V, which is the direction of the greatest gain from the KS UE. And that is used as a beamforming vector in one of the strategies. And then for the angular beamforming, the idea is basically get the highest large-scale fading, which is the AP that is going to provide the highest gain to the UE. And then we select that AP for the communication beamforming. As you can see here, the communication beamforming is basically using the AP with the highest large-scale fading. But then for the sensing beamforming, we are basically transmitting right at the middle of the APs performing the sensing reception. So it's not exactly the best AP, but it's like in the middle of the region where the target might be. So this is the sensing metric. We are adopting this MSE of the product of the spatial frequencies, considering that the angles were estimated using music. So in this work, we basically derived the SINR, and then we are also analyzing the SINR performance for sensing and communication. But then we also decided to estimate the angles based on that SINR and based on the power that we are allocating for the sensing beam, and then compute this MSE. So this is a little bit about the simulation setup. So we have 100 APs, 8 antennas at the APs, and then we have 10 users with 4 antennas each, and we are only considering one target for the simulations. And then we have that regular deployment of the APs in a square grid of 500 by 500. And then we have the total transmission power at the UEs of 24 dBm. And then what we are doing for analyzing this power allocation is that we are splitting equally. I mean, we have a scenario where we split equally the power between communication and sensing, and then we allocate 10% for sensing, 90% for communication, and the opposite, 90% for communication and 10% for sensing. And then we have here the model that we are using for the radar cross-section, and then we ran 1,000 independent realizations to get the results. And then I also have more details here about the path loss. We are using these 3 slow path laws, and that is the model for the large-scale fading. So these are the initial results that we have. So basically, in this picture here, we are allocating 90% of the power from the UE to communication, to the communication beam, and 10% for the sensing. Here we have 50-50, and here we have 10 for communication and 90% for sensing. And then we are basically plotting here the ECDF of the SINR that we obtain for sensing and communication. And then in blue, we have the SINR for communication, and in green, we have the SINR for sensing. And on the solid line, we have the SVD, and on the dashed line, we have the angular beamforming. And basically, what we are basically observing here is that when we have more power to communication than sensing, we see that the communication SINR is higher than the sensing, and it's achieving some good value, at least from our understanding. We have like 90% of the users above 5 dB or 10 dB for communication, but for sensing, as we are allocating less power, we see that it's like a little bit worse. So we have, only 60% above 5 or 10 dB. And then we started increasing the sensing power and diminishing the communication power as we have a fixed total power at the UE. And then we see that the sensing performance is starting to increase and even becoming higher than the communication performance. Up to the point where we allocate most of the power to the sensing beams, and then we see that the sensing is much better than the communication. For now, this is, fixed, but then we also are now investigating some more smart allocation of power using some optimization. So this was just a fixed strategy with fixed beamforming and fixed power, and now we are enhancing this algorithm. And here we have basically the ECDF of the MSE of the estimation of the angles from music. And this is basically showing that, unfortunately, we don't have any comparison here. But we just wanted to analyze these performances and basically if the values would be good or not from the uplink sensing, because imagine that in this scenario we have the UE transmitting the sensing beams, and they have much less power than the APs, right? And usually much less antennas. And then we wanted to see about the results, and then as we are increasing here the power allocated for sensing, we see that the SVD, which is like the most ideal, would have the best performance for sensing, as we are increasing here the power. Okay, so for the conclusions, this is what we wanted to arrive at, which is basically analyze whether it would be feasible or not to have the UE transmitting the sensing symbols instead of the APs. And then we saw that we achieved good SINRs and also MSE. And then the UEs are now splitting the using two beamformings, right? One for communication and one for sensing. And then the idea now is to enhance the power allocation and also the beamforming strategies. And then we are starting some max-min SNR optimization problem, at least this one, to optimize the power and not have fixed power allocation for sensing and communication. Yep, and this is just some acknowledgement for Ericsson, CNPQ and FunCaps and CAPS. Okay, thanks.